Hello everyone, in this video I'll be going over solutions to problems 1 through 3 in Weekly Contest 251. So for the first problem, you're given a string and each character will map to an integer. And you basically need to sum up all the numbers inside of it and perform that k times. So the only clever observation you have to make here is that k is at least 1. So when doing this initial conversion, you don't need to convert it to 9,999 because then you could have a 100-digit number, which is just impossible to work with. You can just perform the first transformation while you go through this, and while you go through the string, and then sum it up, and then perform it k minus 1 times. So this is how you implement it. You first just perform that first transformation. So you go through every character, you get the number that it maps to, and you add 1 here because A equals 1, B equals 2, and then you add the digits of this character to our sum. Then you perform this operation k minus 1 times. Notice you start at I equals 1. And every time you perform the operation, you can simply, to add up all the digits, you can simply add the last digit and then remove the last digit, and this will add up all the digits. And then, yeah, then at the end we can just return. And if we submit this, it gets accepted. Okay, so for problem 2, you are given a string which represents a number and an array that represents what numbers map to which number. So 9 at index 0 means that every 0 in this string will map to, you can change that to a 9, and so on, like this. And you can mutate any substring. So a substring is just one contiguous sequence of characters. So you want to essentially, what they want you to do is they want you to, given this number, mutate a substring so that you get the largest number. And like the first problem, you only need to make one clever observation as well, and that is that whenever you can change, since a substring is just, it has to be contiguous, so you can't change this number, then this number, it has to be all connected. So you have to change, you can change these two numbers, or just this number, or these two numbers. And the other observation is that whenever we want to mutate a substring, we want to do that as early as possible, because let's say in our array here we have, I don't know, it doesn't really matter, but let's say 1 maps to 9. So because 9 is at index 1, that means 1, you can change every 1 into a 9, or we can use 2 for this example. So let's just say every 1 turns into a 2. That's good for us because that makes number larger. And we just want to apply that to the first subsequence that we can, because let's say we can change a 2 into a 9. That means we can either end up with changing this 1 into a 2, so 2, 3, 2, or changing this 2 here into a 9, which is 1, 3, 9. It's obvious that even though we can only increase 1 to 2, this is still favorable because we are doing it at a higher place in the digits. So changing the 1 place to a 9 doesn't really matter. So essentially what we want to do is we want to find the first spot starting from the largest digit where we can perform a mutation that increases the number, and then just mutate as many favorable mutations as we can. So let's say 1 maps to 2. Perfect. We know we want to start mutating from 1 right away. And if 3 is favorable, let's say 3 maps to 4, we'll also change that. Then our final answer, and we'll continue and mutate as long as it's favorable, and once it's not favorable, we stop mutating. So our answer will be the first segment of the string, so whatever that is, our mutated segment, where we perform changes, and then the rest of it where we don't want to mutate. And we just want to mutate the earliest segment that's possible to increase our number. And so you can just implement it like this. So we will go through every number inside of our string, and I just get that as a number right here. And if we can turn it into a favorable, if mutating is favorable, so this change is greater than the actual number, because change of a number is what we can change that number to. So if it's greater, so that means it's a favorable change, then we will perform our operation here where we add the first part of the string, this part, and then we so while mutating it is favorable, so greater than or equal to, then we will want to append the mutated number and go on to the next number. And this just prevents out of bounds exception, and yeah, this just grabs the value of the next number in our string. Then at the end we will append the the ending bit here. And then that's our answer. And if we cannot make any favorable mutations, we will just return our original number, as you can see in this test case. And yeah, so this is an accepted solution. So for problem 3, you're given an array of students and their answers, and an array of mentors and their answers. And basically you need to pair each one of them up with another one from the other array, such that their compatibility score is maximized. And their compatibility score is calculated by simply taking the number of answers that they share. So for example, if you pair this student with this mentor, they share 1 on the first, and they don't match the second, but they do match the third, so they share 2 answers, so their score would be 2. And so the key thing here to realize is actually that there can at most be only 8 students and 8 mentors. So we can pretty much just brute force this solution, and we can do that by seeing. It's easier to visualize this if we draw it out. So let me just draw this out here. So what we can do is we can just pre-calculate the score of each student if we pair them with each mentor. So for our student 1, 1, 0, this guy, we will compare him to each mentor. So for the first mentor, you get a score of 2, and for the second mentor, you get a score of 0, and the third mentor is 3, and for the second student, 1, 0, 1, you will get 2, 2, and this matches, and nothing else matches. So we will get 1, And then if we repeat the same process for the third student, we will get 2, 3, and 0. And now we can simply see that to maximize the pairings, we just need to choose the arrangement of numbers from each of these, which add up to the most and have different indexes. So because this 3 here means that we pair the student with this mentor. So if we do that, we cannot pair this student with the same mentor. So that doesn't work. So since we know the score of pairing with each mentor, we just want to choose the mentors that give us the best score. So in this case, we will choose this 3 here, this 3 here, and this 2 here, or no, sorry, and this 2 here, because these are all different indexes. So you will pair this student with the third mentor, this student with the second mentor, and this student with the first mentor, because this is the first, this is the third, and this is the second. And it's just important that these indexes are different. So you cannot pair this guy and this guy. That's impossible because you cannot assign the same mentor to different students. Yeah, they're one-to-one. And then, performing some quick calculations, we so first of all, this computation of comparing each student to each mentor will be very fast because at most there can be 8 students and at most there can be 8 mentors. So if you pair them up, at most there's just 64 combinations, because for each student you're pairing him with each other mentor. And then checking their score is just really fast as well, because at most you just need to check 8 different numbers. So yeah, so first we can just compare each student, and then we will have this sort of array that looks like this. We can save our computations in array, and we just need to choose one number from each row and make each column, like you can't choose 2 numbers from the same column. So we can choose this number, and this number, because they are all in different columns, and we just choose one number in each row. And looking at this array, it's essentially an 8 by 8 matrix. So for the first row, you have 8 choices. Then for the second row, you have 7 choices because you cannot choose the same column as your first. So if you chose this one, you cannot choose this anymore, and etc. So essentially what we would need to do is we just need to check 8 factorial like combinations, and 8 factorial is about 40,000. I think it's like 40,200 something. It's around 40,000. So this is easily doable. So we just check 40,000 combinations, where we choose one guy here, and then we choose one guy out of the 7 here, and etc. So that's the solution. So if we look at how that's implemented, so this just first calculates this array of scores. So we have an m by m array to because we will need like each student to be paired with all the different mentors, and we know there are going to be m students and m mentors. So we go through every pairing. So for every student, we pair them with every mentor, and we just calculate their score. And then next what we do is we just permute all the different combinations of these columns. So essentially what we do is we have a list of integers representing the columns that we can still pick, and we will just go row by row and pick a column that is inside of our columns that we can still pick. So in our main body here, we will just first add every column as an option, and then we will permute it. And so every time we will go through the list of options, and we will remove one of the options, and then try out that combination where we remove this option, where we take this option, because we will add their score to the sum. So this is the score if we, let's say, took this column of this row, and I just used the size as the row because it's arbitrary whether we start from this row and work our way up or this row and work our way down. But you could also just have another integer here, like that you can use for the row. So this just permutes the and then it calls itself. So yeah, and then after you explore this possibility where you take this number, you add it back so you can explore other possibilities. And so this will just permute all the combinations. So it'll try taking this number and then explore these possibilities. Then it'll put this number back and then take this number and explore the possibilities, and then etc. So this permutes all the combinations of choosing different columns in each row. And then what we do is when there are no more rows to choose from, we just see if this permutation is a better one than we have already. And if it is, then we set that as our answer. And we have a global variable here, so we can just return that. And we set it to 0 before we do this permutation. And this approach works and it gets accepted for the reason I said above, because essentially you are just checking 8 factorial combinations, so it's not that bad. And so yeah, so that's about it for this video, and thank you very much for watching.